All right, I'm going to see if I can trip over myself a little less. So, spiking neural networks are defined as, or are defined by, are differential equation models. They are defined by differential equations, right? So when we looked at the artificial neural networks, right, we talked about units connected to other units by weights, right? I don't like 1. Let's have 3, right? And then we had a rule for assigning values to the to some of these units, and then propagating those to other units based on the weights, right? We had rules for a forward pass, and then we had rules for a backward pass to update the weights. So with spiking neural networks, they are inherently time dynamic things, and we describe them with differential equations that describe their time dynamics, right? By time dynamics, I mean how they behave in time. And I'm out of room, right? How they behave in time. And then we simulate them, okay? And this is sort of an inherently time-aware simulation, right? We're going to be stepping through time and updating the state of each of our neurons according to the equations that describe their time dynamics, right? So we're not going to get into how you solve differential equations because this is not a math class or a modeling class. We're not going to get into numerical simulation, right? Like if I started talking about RK4, I would be terrible, right? And we're not even going to get into discrete event simulation, which is what we'd have to start doing if we're going to have to talk about spiking, right? So, basically, in general, each neuron in a spiking neural network has a membrane potential, a voltage, right? V. And the time evolution of V is one of the variables that we're going to track, right? So we're going to look at equations that describe dV over dt, all right? When the voltage crosses a threshold, an action potential or spike is emitted, hence spiking neural network, right? The membrane potential then resets afterwards, right? So membrane potential goes up, spike, reset. And so actually, technically, there's a little refractory period down here where the neuron will not spike, but we're not really going to worry about that in a lot of our models, all right? And I really probably should have drawn the spike much narrower. It is a very rapid thing, all right? So those spikes are how the neurons communicate, basically. These rapid little rises and falls in that potential are the way that neurons exchange messages in a spiking neural network and in the brain. So spikes, again, are very, very quick, right? So if we kind of look at my crappy drawing of a spike, right? This little spike right here is a very short-term event, right? It does not take a long time to happen, right? So we go along, and then voltage shoots up, and then it gets pulled down very, very quickly, and those spikes are extremely, extremely narrow, right? Spikes are quick enough that a lot of the time, and especially with spiking neural networks, we can kind of get away with thinking of them as discrete events, right? So instead of trying to model that short-term, transient, extreme voltage fluctuation, we can just sort of go, and treat it basically as an event, right, that happens at a specific time, t, right? So voltage goes up, we mark the spike time, and then we reset, all right? And again, SNNs can be very efficient because they only, sort of circle the asterisks here, perform communication or perform computation in the sort of instance that these spikes occur, right? And again, because spiking activity is sparse. Neurons spend most of their time not spiking. And I guess I don't know if, so I've been I've been tinkering with these slides quite a bit, and I've had to restart these recording a time or two. So I don't remember if I said, I don't remember if I recorded. Those spikes are very hard to model, right? If you want to write down a differential equation that can accurately capture that spike, you absolutely can do it, but it takes a lot more math and biological rigor than we want to get into right now. And for the kind of computation we want to do, we don't care, right? So we're going to deal with models that basically, that don't model the spike directly mathematically, but that, just say, when you cross this threshold, we declare you as spiked, and then reset you, okay? That's what we're going to do. So there are a lot of different models. Like capital R real, capital N neuroscience has produced a plethora of models with very different levels of fidelity, right? That capture very different parts of what a real neuron does, and that have very different requirements. Some of them can be can require very sophisticated simulation to kind of capture all of the time dynamics correctly, right? We're not going to worry about most of those. Again, we're not neuroscientists, we're AI guys, right? So we are going to look at a very simple model that has the convenient property that can be simulated very efficiently and written very easily. And that is the Leaky Integrate-and-Fire neuron. So Leaky Integrate-and-Fire is real simple, right? Absent a spike or current, it exponentially decays to a resting potential, right? So here is time, and let's say that this is the resting potential. If you drive it to some other voltage and let it go, it just sort of exponentially decays, right? So absent a driving current or spike, it will just exponentially be drawn from wherever you let it go to its resting voltage. It generates a spike. Oh, wait. Okay, yeah, if a combination of spikes or current drive it over its threshold, it emits a spike of its own and then resets. So, right, if you have, down here is the resting current, and then up here is the spiking threshold. If you have, let's say, a driving current applied, and it's going to go up and up and up, and when it crosses the threshold, right, we declare a spike at time t, and then reset it. Okay, up and up and up, spike, reset. It's a very, very simple model. All right. Oh yeah, so this is a good, if extremely technical overview of these things. And then this preprint, and I probably wouldn't recommend that you read this, because it is deep in the differential equations modeling. This is actually kind of interesting. It's a preprint. I didn't have time to read over it very carefully, but this is a paper on integrating LIF neurons into TensorFlow code, which is super cool. But I didn't have time to step through it and try it and be able to talk about it intelligently. But if you get through this whole chapter, and if you feel like this whole lecture, I should say, and if you feel like your math chops are up for it, coming back and looking at this paper could be an interesting thing to do. I certainly will. All right. So the model formally looks like this, right? And again, I apologize. These things are defined in terms of differential equations. In a slide or two, we're going to see code, all right? And I think the code will be pretty easy to see. Pretty easy to understand, I should say, right? So right here is dV dt, right? There is the change in voltage through change in time, right? So the Leaky Integrate-and-Fire, one of the things that makes it quote-unquote simple is that it has one variable, right? There's one dynamic variable we care about, and that's V. That's it, right? Another thing that makes it simple is that a lot of the terms that influence V are fairly simple. Each one of these I's is a current, right? We have current from leak being the thing that pulls it down to its resting potential. We have current from spikes, which are usually going to be treated as atomic deposits of energy, right? When you get a spike, in the time step you get it, you add a certain value, and that's it. There's no sort of time dynamics of that. It just happens at a certain point. And then there's current. Excuse me. And there are a couple of different models we could use for current. Some are more reasonable than others. But current could potentially be constant, right? So we have leak, which is a little bit complicated. It's this. We have spikes, which is just some constant value during the time frame a spike occurs, otherwise 0. And then we have current, which might also be as simple as a constant value, right? So this thing plus 0 or 1 plus a constant, more or less. This Cm over here is the capacitance of the neuron, right? Neurons, so I thought about talking about like having a little picture of the neurons. Basically, we're talking about the amount of energy that it can store. Oh, let's have a little axon. Whee, I'm the axon. And let's have a little dendritic arbor. Whee, dendritic arbor, right? We're talking about the capacitance across the cell membrane, right? Basically, you can kind of think of the thing a little bit like a little capacitor. I'm trying to cast my mind back. So that's the capacitance is also related to resistance, which is related to energy flow across the membrane, and I forget all of the details of that to talk about it intelligently. So this little tau right here, so this is basically just sort of a fairly typical description of decay to a rest voltage in the language of differential equations. This tau is a time constant that controls the time scale over which the leak will act, right? Larger tau, right? As tau goes up, the time factor becomes larger and the leak will more slowly pull to the resting potential. There we go, right? So very large tau, right? That means that our leak takes a lot of time to pull. That means that the time... Very large tau means that sort of the time scale of our leak current is very large, which basically means it's very slow, right? We're saying it will be very slow in pulling down to the rest potential. Very small tau means our leak current operates over very short terms, which means it very quickly pulls our voltage down to our leak term. Okay? All right. So if we move stuff around and then we substitute and then we drop, so we drop the spike term because it's usually 0, and we drop the current term, we assume that we're not applying a current to our neuron, we get this very simple little equation, right? This is the equation for how our, this is the update equation for our neuron when it's not getting spikes and not receiving current, right? So the behavior in time, absent spikes or current, is to just gently decay to your resting potential according to this time factor. And we can translate that into some fairly straightforward Python code, which we'll get to in a minute.